Okay, let's get started. So the last few weeks, what did we do? We looked at this optimal transport problem. We wrote down dual formulation, turned it into a different optimization problem that looked like a completely different problem at first blush. But out of that, we managed to kind of work out the structure that our optimal map somehow looks like the gradient of a convex function. Today we're going to change gears a little bit. We're going to be using really the same techniques we've been using over the last week or two. But to show that while we're not directly solving an optimal transport problem, not only can optimal transport maps be expressed as the gradient of a convex function, you can do something very similar for a large range of vector fields. So this is going to be like a factorization result. It's known as Brittany's polar factorization theorem. Okay. Brittany was really motivated by problems in fluid dynamics when he worked on this. We're not really going to talk here about those connections. Maybe it's a good class project if someone's interested in going deeper into that. But I want to see how this relates to the optimal transport techniques and what comes out. And you know that factorizing things is useful sometimes, right? You've got lots of different matrix factorizations that you've studied. And they're useful for studying the structure of a problem or building an efficient numerical methods for problems, various things. So here we're not trying to factor matrices, we're trying to factor some kind of vector valued mapping. So this is going to be the idea that given a reasonable vector field, we can factor it, not quite as the gradient of a convex function, but as a composition of a gradient of a convex function and some other measure-preserving rearrangement. So we could take any vector field that you like and rearrange it so that it looks like the gradient of a convex function. All right, so this is the result. Let's let omega, being a subset of Rn, be open and bounded. Okay, all with a non-ridiculous boundary. Okay, and we're going to take any vector valued mapping. So this takes our domain and maps it onto something in Rn. And again, this is something that's reasonable. So we're going to say it's non-degenerate. It should be in L2. Vector valued mapping. Okay, what do I mean by non-degenerate? So what I mean by non-degenerate is that we're not going to take a set that has zero measure and map it onto something that has positive measure. Okay, so in other words, if something has zero measure, then it originated from a set of zero measure. Okay, so that's what I mean by non-degenerate. Now this theorem says then there exists a unique convex function, C. I guess by unique it really means going to be unique up to additive constants, right? Because I said we're talking about the gradient of a convex function. So if all we care about is the gradient, you can always lift things up and down. So there's a unique convex function, C. Okay, so unique, we'll say up to additive constants. Okay, and there's a measure-preserving rearrangement. Okay, so S takes omega back into omega, just rearranges everything. such that we can write R of x is the gradient of C composed with S of x. Okay, so if R happens to be an optimal transport map, then we could just take S to be the identity map, and we knew that an optimal transport map can be written as the gradient of a convex function. Now, what this is saying is we've got to take omega and sort of rearrange it, relabel it a little bit. But we can find a way to rearrange it and relabel it so that at the end of the day, R is effectively the gradient of a convex function. So we're going to look at, OK, how do we derive a result like this? It'll use really the same techniques we've been using the last couple classes. I'll show a little bit how it's maybe related to some other factorizations that you've probably seen before. And also talk a little bit about how we would maybe interpret this rearrangement S. OK, so here is why, first of all, why this works. Again, the interpretation of this arrangement X was really, which we'll get to a little later, was really Brenier's motivation for studying this problem in the first place. All right, so we want to use the same techniques we did before. So let's go back to our dual problem and just see if we can tweak it a little bit to make this pop right up. OK, so we want to try to modify our dual problem. I'll say our transformed dual problem, because we transformed it to make it a convex problem. OK, to work with this. All right, now we know things already. We know that we've done a really similar problem to this, where S was equal to just X, the identity map. And we kind of know how this function, how these convex functions popped out there. So, you know, in some ways you can sort of guess at how you might want to modify this problem in order to make all of this fall out. So let's try this. Let's try to minimize what I'll call L hat. Okay, we're going to be integrating over our set omega. Okay, and now instead of phi of x, I'm going to use phi of the vector field that I'm actually interested in. So phi of r of x plus c of x, all right, dx. Okay, and we're going to do same constraints that we had before. So subject to phi of x plus c of y is greater than or equal to x dotted with y. Okay, for all appropriate x and y. All right, so we can do a lot of really rigorous arguments here. I'm not going to go through all the rigorous details of them, because as I write down sort of a lot of the summary, you're going to believe me, because I hope, unless you were sleeping through the last couple classes, because we've done exactly these arguments before. You know, other than renaming some variables, we're really making the same argument that we did last week. Okay, so same arguments as before. I'm going to assume that phi and c are a convex dual pair, right? So take a given phi and c that's feasible. I replace it with a convex dual. It's still going to be feasible. And just like we did before, we can write down the value of my objective function and show that it only goes down if we take convex duals. OK, so I'm just going to say, without filling in the details, as before, we can assume that phi and c are convex duals. Okay, so the feasible set is not empty, right? just like it was before. We can easily write down functions on a bounded set that are going to satisfy this condition. We can take convex conjugates of it. That's no big deal. Then our second issue with minimization is, are we actually going to have a finite minimum or infimum? Is this thing bounded below? Is L hat bounded below? Okay, so let's take L hat of phi and psi. What do we know of it? Phi at any point plus psi at any other point, right, is greater than or equal to the dot product of these arguments, right? Px plus pcy greater than or equal to x dot y. So right away I can say this is going to be greater than or equal to, now instead of x I have an r of x dotted with, okay, now another x. And how do you place bounds on an object like that? Cauchy-Schwarz, exactly. Okay, so this is greater than or equal to minus the square root of, okay, we integrate r of x squared, and we integrate x squared. Which is finite, right? We started by assuming that omega was bounded. If omega is bounded, then this integral is certainly finite. And we started by assuming also that R, the vector mapping we cared about, was in L2. Right? So I'm not assuming that R is bounded necessarily, but I'm certainly assuming that it's in L2. So this integral is finite. Okay, so this is finite. Okay, since R is in L2, and omega is bounded. Okay, so right away we get there is a finite infimum. Okay, infimum is well defined. Our next question is always, okay, we've got an infimum. Is it attained? Is it a minimum? I'm going to basically just tell you the answer. That the answer is yes. And the reason why is exactly the same reason why that it worked before when we were doing the optimal transport problem. Right? We wrote down, okay, we've got an infimum, so we can write down a minimizing sequence, make some argument that it's equicontinuous and uniformly bounded, just like we did before. And then we say, okay, by Ascoli-Ar's law, we're going to have uniform convergence to some limit, and that limit is going to be a minimizer. Okay, so I'm not going to write down any of what I said except the punchline. As before, there's also a minimum. Okay, so this stuff so far not different than what we did last class. Now what we really want is somehow to try to extract something that we can call S from this. All right, we're given R. All right, we kind of can guess where C has probably come from given the problem that we just wrote down. How do we extract some kind of measure-preserving mapping S from this and write down this relationship? So that's what we really want to do. So this is our question. Can we extract a measure-preserving map S from this problem? Okay, so in other words, what do I mean by that? We want to find some s such that, okay, our usual condition that we write down, if I take any function h and integrate it, it should be the same thing as if I integrate h of s of x. Okay, for all h that are, say, C0 on, let's say, omega bar. All right, again, I'm just trying to reuse what we've already done before, because why do the same work twice if you don't have to? We made an argument very similar to this last time by perturbing our optimal phi and psi. So let's do that again. Let's try perturbing our optimal phi and psi. Okay, again, as before. And again, I'm going to give you just the highlights of this and not fill in all the details, because you know how to fill in the details. So we had psi epsilon was equal to psi of y plus epsilon h of y. And phi epsilon was going to be a Legendre transform of this guy. Okay, so phi epsilon of x is the supremum over all y of x dot y minus psi epsilon of y. Okay, we know this is admissible because this is a Legendre transform of this, and that automatically gives us our admissibility conditions. Okay, so this is an admissible pair. Okay, but what have we done? We've taken the optimal pair and we've perturbed it, so what we've got is probably not optimal anymore. Certainly we haven't caused the objective function to go down by doing this. Okay, so as before, we can say, let's look at L tilde of phi epsilon psi epsilon minus L tilde of phi and psi. We'll divide out the epsilon like we did before. Yeah?
Is tilde the same operator as L?
I guess I called it L hat, sorry. Thank you. Sorry, it was L hat. Okay, what do we know? We know that this guy was the minimum. This guy is larger or the same, so we've got something that is positive here. Okay, and same game as before. We're integrating. We have a phi epsilon of r minus phi of r. Okay, over epsilon. We have a psi epsilon minus psi. Okay, again, just like before. Psi epsilon minus psi is epsilon h. And we divide out the epsilon, so we've just got an h. So again, just like what we've done before, we need to make some argument about what this integral is going to do in the limit. So I'm just going to give you the formal argument, and the details we'll go through again, just like we did before, using the dominated convergence theorem. Okay, but let's try to argue formally at least what we think this term is going to approach. So what do we have? we know that x dot y minus c of x, minus c of y rather, this is what's going to show up when we try to compute phi. And this is maximized when y is equal to the gradient of phi. Okay, so now I want to use that idea to write down phi of r of x. Okay, so phi of r of x, okay, this is the supremum over all y. Now my argument is r of x, so r of x dot y minus c of y. This should be a y. Okay, and now we know when this is maximized, right? We said this is maximized precisely when y is the gradient of phi. Okay, so this is going to be r of x dotted with the gradient of phi of x minus c of the gradient of phi. Sorry, I need to be careful here. I'm not working with x, I'm working with r of x. So y is equal to the gradient of phi evaluated now at r of x. Gradient of phi of r of x minus c evaluated at y. Again, this was maximized when y was the gradient of phi, now evaluated at r of x. Okay, so this is what we'll be able to put in place of phi. Then we need to also compute, or at least estimate, phi epsilon, right? And we're going to care what happens as epsilon is small. Okay, so if we want phi epsilon of r of x, that means we're going to be maximizing x dot y minus c epsilon of y. So that was minus c of y minus epsilon h of y. Okay, we want to maximize this. It's almost the same as maximizing this right here. So here I have a function that is continuous. And we know that it has a maximum, right? And we can, almost everywhere it has a unique maximum. We made that argument last time. Okay, so assuming it has a unique maximum, then if I perturb it by a small amount, this is also going to have a maximum, and the maximum will be close to grad phi, right? So take something with a strict maximum, we perturb it a little bit, the maximizer is stable. So it just moves a little bit. So this is going to be max when y is equal to grad phi of x plus something small. Okay, so if I want to compute phi epsilon here, right? Phi epsilon is the maximum of this, so it's equal to this when y is grad phi plus something small. So phi epsilon evaluated at r of x is going to be r of x dotted with the maximizer. The maximizer is grad phi of r of x plus something small. Okay, minus c evaluated at the maximizer. It's grad phi of r of x plus something small. minus epsilon times h at the maximizer. Okay, so we have something close to what we've got over here, right? R dot grad phi of R minus C evaluate at grad phi of R plus some other little bits floating around. Yes? Grad phi of R of X, yes, thank you. Okay, now what do we care about? We care about really the difference between these two things and dividing out epsilon. Again, I'm not going to go through all the rigorous details of this because the rigorous details are exactly what we did last time. But as before, we're going to argue. We argue that. Okay, this limit. The limit is epsilon goes to 0 of this integral that we care about, phi epsilon of R of X minus phi of R of X. Okay, and what happens? We get more or less cancellation of this term, and we get a more or less cancellation of this term. And we're left with this term, and we have to divide out the epsilon. Again, the details I'm not working out here, but you can go back and see how we did them. So this should be equal to the integral of h of grad phi of R of X. Okay, so we get all of this coming to h of grad phi of R of X, right? As before, I could make the same argument, replacing h with minus h, so I would get the inequality flipped around. Right, so we can do the same thing where h gets replaced with minus h. And at the end of the day, we get the equality that we want. We're going to get something like, okay, h of grad phi of R of X is equal to h itself. Okay, so what was our goal? Our goal in all of this was to say, can we pull out of this problem a measure-preserving mapping? We didn't know ahead of time what it was going to be. Like last time, we said we wrote down t equals gradient of phi, and we said we like this mapping. Let's check and see if it's measure-preserving. Here, we're kind of trying to work backwards a little bit and saying we'd like to find a measure-preserving mapping. We're not sure what it's supposed to be, but let's try the same argument and let's see what falls out and what falls out. So we wanted integral of h to equal the integral of h of s of x. And now what's in here is functioning as our s of x. Okay, and now we've just made the argument, minus some of the details, that if I define s in this way, I get a measure-preserving mapping. So we can conclude that s of x, that we now know how to define, grad phi of R of x, okay, is in fact measure-preserving. Okay, so S, in other words, we start with our set omega, S takes omega and maps it back into itself, rearranges things a little bit, but rearranges things in a way that the measure is still the same. We're still, the Lebesgue measure is preserved under this mapping. Yes?
How did you know to write down L hat, that functional, the way you did?
How did I know to write down L hat, the functional, the way I did? So there's probably a couple answers to that.
It seems like it all hinges on that.
It hinges on that, definitely. So there's a couple different answers to that. One is that you can start with some of the motivation that I'm going to talk about a little bit later and try to relate it to an optimal transport problem and relate it back to that. Another way is to say, we have all these arguments about how to build some kind of measure-preserving map, right? This map T equals gradient of phi. And we did it through this functional L. We're trying to do almost the same thing here. We're trying to pull out another measure-preserving map and relate it somehow to the gradient of a convex function. That was the goal here. So maybe we can take our original L and just, what's the smallest tweak that we could get to it to put this new vector field inside of it that we care about, R of x.
So it was a good guess, essentially.
So in some sense you could think of it as, yeah, this is a good guess, an educated guess, and you might try one or two things. You know, they're not out there magic tricks.
Right.
It's saying, this problem feels like a problem that I've solved before. So what is the smallest manipulation I could do to this problem to stick in this new vector field that I care about? And that's really the smallest. And you know, maybe you put it inside of phi, and maybe you put it inside of c, and it doesn't matter at the end of the day. Things just have different names. Okay, so we've got this nice mapping. And then we can use the fact that we're really trying to factor R here. But factoring R kind of pops right out of this. So now we wanted to factor R. We have this relationship between S and R. We also know that phi and psi are Legendre duals. Which means there's symmetry here in how we can express these things, right? I can take this and express it in terms of the gradient of phi, or I could take this and express it in terms of the gradient of c. And there's nice perfect symmetry here between objects that will live in one domain and the gradient of the other beast. So right away we can write down, well then R of x is equal to grab c of S of x. And this is exactly what our goal was. This is the factorization of R. To say, okay, it's not quite the gradient of a convex function. The gradient of a convex function is a strong statement. There's a lot of constraints on that. But with not too much work, we can rearrange the vector field, and now we get something that is the gradient of a convex function. Any questions here? How do you know the mapping is unique? So it's not necessarily. It's going to be unique in some sort of L2 sense, right? So I've kind of been writing gradient of phi, gradient of c here. We knew when we did this for the optimal transport map, I actually said I could write it down as unique almost everywhere, right? Almost everywhere there's a gradient. Everywhere there's a subgradient. So remember when I defined T last time, I said, as long as I'm in this set, what did I call it, x tilde or something, right? For this full measure set, I have a unique map. Everywhere else, I just pick something. Just pick any element of the subgradient and put it there. So it's almost everywhere unique. So what was unique is this convex function. This convex function is unique up to constants. This guy is going to be almost everywhere. But because when you're checking this measure conservation, kind of, you know, the integral erases what happens on a set of measure 0. Other questions on that? All right, let's do an example in a special case. So let's try to kind of linearize things a little bit. We're going to do a little bit of asymptotics. So let's assume that the vector field I care about is pretty close to the identity map. Okay, so it's like x plus something small. Okay, so call this an example. Let's do the special case of vector fields close to the identity. And we're going to do some asymptotics. Okay, so I'm going to suppose M is just some nice enough, whatever that means, vector field. Okay, and we're going to write the guy we care about is x plus epsilon m. So close to the identity, but we've perturbed it a bit. Okay, and we're going to apply the polar factorization theorem to R. Okay, we know that we can write this as grad C of S of x. Okay, for some convex C and measure preserving S. Right, this was our polar factorization theorem. Okay, so now let's make some educated guess about the structure of this thing. We're close to the identity. So let's first think about what we would do if we were near the identity and ask how would we factor or decompose the identity map. So if epsilon is 0, all I have is r of x equal to x, and I wanted to do this, what would you pick for s of x?
Inverse of the gradient of c.
The inverse of the gradient of c. So think even simpler than that. We're trying to, so yes, but let's try to write this in as simple a form as we can. We need so we need a measure preserving map here. What's the simplest measure preserving map you can think of? The identity, right. So we're working with the identity map. So, in order to get a nice structure for the identity map, we shouldn't have to rearrange things too much, right? We should be able to use S naught of x equal to x as the identity. And then what's my convex function? It's quadratic, exactly. So I want a convex function here whose gradient gives me the identity. So we can do that using x squared over 2. Right? This is the very simplest factorization of anything that I could come up with. Right? Simplest convex function you can think of, quadratic. Simplest measure preserving map you could think of, just the identity, the map that doesn't move anything. Okay? And indeed, we're going to have that C naught, grad C naught of S naught of x gives us back x. Okay, so that's what we would plan to do if we were working just with the identity map. Now we've perturbed the identity map a little bit. So we're going to play the game that you do in asymptotics. We're going to make an ansatz that s of x here is going to be pretty close to this s naught, and that the convex function that I want is going to be pretty close to this quadratic here. Okay, so let's make this ansatz. Okay, that s of x is going to look like x plus epsilon times s1 of x, okay, plus higher order terms. Okay, and my convex function is going to look like x squared over 2 plus something that's of order epsilon plus higher order terms. Okay, and now we're going to substitute this in and see what we get. So we know exactly that r of x is equal to grad c of s of x. Okay, so from the polar factorization of r, okay, r was equal to x plus epsilon times m. Okay, this should now be equal to grad c evaluated at s. Okay, so this is going to be grad c. How will I call this? Do it like this. So gradient of this is the identity, which we're going to evaluate it at s. So that's going to be x plus epsilon s1 of x plus order epsilon squared. That's the first term. Gradient of this evaluated at s plus epsilon times the gradient of c1 evaluated at all of this. Okay, plus higher order terms. Okay, so we can simplify this a bit. I'll take my order 1 terms. That's just the identity. That's good. That's what we should have coming out as our order 1 term, because, I mean, we've already assumed that. We're going to have our order epsilon terms. So here I have an S1. Okay, here I have epsilon times C1 of all of this. Okay, so this should, C1, if this is a nice differentiable function, everything's nice, I should get gradient of C1 evaluated at S1 of x. Okay, plus higher order terms. Okay, so this suggests that for this to work out, m of x should have this structure. Okay, it should be equal to S1 plus the gradient of C1 evaluated at, sorry, this should just be at x. Okay, so this is one thing that we're going to expect. If the asymptotics are to work out, this should be true. Okay, we know more than this. We know also that S is not just any function. S is a measure-preserving rearrangement. Okay, so we also know that S is measure preserving. Okay, so assuming everything's nice enough, what's a simple way of characterizing a measure-preserving rearrangement or change of variables, if you will? The determinant of the Jacobian is 1, right? So again, it's your change of variables formula from calculus, right? You do the change of variables, the determinant of the Jacobian of the map pops up in there, and now you say, but I don't want this messing with my measure at all. I want it to keep things the same, so I just want it to be equal to 1, so I'm just multiplying by 1. So from our change of variables formula, we know that 1 should be equal to the determinant of the Jacobian of S. Okay, so come over here. The determinant of the identity is just the identity matrix. So this is the determinant of the identity plus epsilon times the Jacobian of this thing. Okay, plus higher order terms. Okay, so I have this matrix on the diagonals. I have things that are order 1, 1 plus epsilon times, derivative of the first component with respect to x1, and then the next is derivative of the second component with respect to x2, and so on. On the off diagonals, I have things that are going to be of order epsilon. Right? Off diagonals, this is 0. So if I want to try to write this out, again, I don't care about exactly what this is. I just want to collect the order 1 terms, the order epsilon terms. Okay, the order 1 terms are just multiplying out the diagonals of this guy, 1, which is good. That's what we want to get. Epsilon times something. Okay, we're only allowed to pick out one of these terms when we multiply things out. Otherwise, things jump to order epsilon squared. So what are we going to get? We're going to get precisely the diagonal components of this Jacobian added together. So this is going to be nothing but the divergence of S1. And lots of other things that are messy that we don't have to work out, but they're smaller. Okay, again, we start matching terms. So order 1 terms match. This is good. We move to order epsilon. We've got nothing on here, so we'd like this to be equal to 0. So we expect that the divergence of S1 is equal to 0. Okay, so what have we done? We've started with just any old vector field that you like that's kind of nice enough. And we've said, I can decompose this somehow. I can take the vector field you gave me, which there was nothing special about this, and I can write it as the sum of 2 things. One is the gradient of a function. The other one is something that's divergence-free. Okay? Have you guys seen this before? Nodding. Do you remember the name of it? Helmholtz, yeah. Okay, so what have we done? We found that we can decompose a gradient field, and basically an arbitrary, not gradient field, vector field, into the sum of a gradient and a divergence-free field. So somehow inside this polar factorization theorem is the Helmholtz decomposition. You can think of polar factorization being like a nonlinear generalization of Helmholtz. And if you decide to linearize your polar factorization theorem, Helmholtz falls out as sort of a special case. So we can think of it this way. The Helmholtz decomposition is like a special case or a linearization of polar factorization. That's kind of a fun example of seeing this connect to other things that you learn in math and physics. But somehow there's a lot more buried in this polar factorization theorem. Yeah?
Do you know off the top of your head if carrying this to order 2 gives you something meaningful?
I'm not sure what happens if you carry this to order 2. You're welcome to try it and let us know if it gives you something meaningful. It gets a lot messier if you carry it to order 2, certainly. So order 1 gives you something very elegant. Order 2, this is going to be less elegant at order 2. But there might be something interesting there. Or, it might be something in 2D at least where you can pull out something interesting. Okay, so we got the theorem. We've seen some kind of interesting connections with other things that we know. I guess another question is, and this comes down to interpretation a little bit of these mappings S, is can we relate it back to an optimal transport-like problem? Right? I basically started with the dual formulation to get this out, but when we did optimal transport, the dual formulation came from some other problem, some other big optimization problem. So this is another question here. Can we take this polar factorization theorem that came from something that looked like our dual problem and relate it back to another optimal transport-like problem? Okay, so here's my next question, is can we kind of work it backwards to relate polar factorization to some kind of optimal transport-like minimization problem? Okay, so what did we solve? Let me just write down the dual problem like thing that we solved. We looked at this. Okay, so we did the minimum of phi of r of x plus c of x dx. Okay, subject to some conditions. Phi plus c is greater than or equal to x dot y. Okay, so how did we get this, right? I mean, we said it's kind of an educated guess, but we basically started with our dual problem under the simple case where our measures are just the Lebesgue measure, where our domains are all the same, so we're integrating over the same thing. And we just did the simplest thing we could think of to introduce R into here. So now let's see if we can really make this look more like our dual problem, and not have this R sitting inside of here, but having it sitting somewhere else that actually makes it look like our dual optimal transport problem. So let's make this look like more like dual problem star. So the second term here is fine. We've got a psi times something. What do we want rather than this? We want phi evaluated maybe at x or at y, whatever. But we're allowed some other freedom. We don't have to integrate against the Lebesgue measure, right? We could change the measure that we're integrating against. So that's where I have room to manipulate things. I can change the measures. Okay, we have freedom to change measures. So what I'd really like is phi integrated against a measure mu, psi integrated against the measure nu. All right, psi already looks good. So it seems like a good idea to just let nu be the Lebesgue measure. Yes, that puts this term in the right form. It just says don't do anything to it. So let's let nu be the Lebesgue measure. Okay, on the other hand, I want to try to get this r outside of here and replace it with a measure that is being integrated against. Okay, so we want a measure mu such that, say, let's say this, h of r of x dx is equal to h of y d mu of y, say for all h. Do you know what another name is for the measure that does this? We actually did this on the very first day of class, I think. We said, okay, we start with a measure, the Lebesgue measure here. Now we have some kind of function or mapping that converts it into a different measure, right? It's the push forward, exactly. So mu is the push forward of the Lebesgue measure through this mapping R. So let's let mu equal push forward of Lebesgue through R. Okay, so in this language or notation, we are studying okay, so phi of r of x dx becomes phi of y against d mu. And my other integral is unchained psi of x against dx. And we decided to give the Lebesgue measure another name and call it nu. So this is the same as integrating against nu. Okay, it's subject to some constraint. And this should look really familiar, right? This is exactly our transformed dual problem that we looked at when we studied optimal transport. This is exactly our dual problem star. Right? Now, with an appropriate choice of our measures mu and nu. And that means there's an optimal transport problem behind this, right? This came from, this problem, the first time we wrote it down, came because we were trying to solve an optimal transport problem with a quadratic cost between the measures mu and nu. Okay. So this is exactly equivalent to quadratic cost OT, optimal transport between mu and nu. Okay, nu being the Lebesgue measure. Okay, so we started with this vector field R that we're trying to factor. We use R to define a measure mu. We look at the push forward of the Lebesgue measure. And now what are we solving? We're solving, by doing this polar factorization, we're equivalently solving minimize, okay, x minus t of x, so quadratic cost optimal transport against the measure mu, with the condition that the push forward of mu is equal to our Lebesgue measure. So somehow when we're doing polar factorization, it's equivalent to this. I've lost the mapping S somewhere along the way. It's not sitting here anymore. And we knew that the mapping S was kind of critical to doing this factorization. The mapping, the vector field R is certainly in here. It's embedded in this measure mu. But let's just think about this a little bit and try to see where did S go. Okay, so where did S go? Right? And also the gradient of C, because that came up in the factorization. So where did S go? And the gradient of C. So those were the two terms that came up when we tried to factor R. All right, so let's just draw a little picture here and try to figure out where everybody's going. So we have this measure. This measure is easier to deal with because it's the Lebesgue measure. And this is where we started. We started on our set omega with the Lebesgue measure, which I've given the name nu in this problem. And we were given some kind of mapping R. That's what we started with. It takes this somewhere. It takes omega and maps it to whatever. And what's the appropriate measure to be working with over here? Our push forward nu, yeah, which we gave a special name. We called it mu. Okay, so we started over here. We started with, we have a domain omega. We're working with the Lebesgue measure. You gave me a vector field that maps omega to whatever it maps it to, and we decided to define the push forward of this measure as mu. All right, we did some polar factorization. So when we started with the thing that looked kind of like our dual problem, but tweaked it a bit, it said that we could take this mapping and factor it, right? We could write it as the gradient of C composed with S of x. Okay, so in other words, we could take this and map it through S, and then take the result and map it through the gradient of C, and get the same thing. All right, what do I write here? What set is this, first of all? It's omega. Yeah, so S was just a rearrangement of omega, right? A measure-preserving rearrangement of omega, and we still preserve the Lebesgue measure. Okay, so here we use the fact that S is a measure-preserving rearrangement. Sorry? Why did we need the rearrangement? So we needed that when we were doing polar factorization. In order to write it, our vector field R as the gradient of a convex function, we had to rearrange the domain first. So any old mapping you give me, I can't write as the gradient of a convex function. I have to rearrange things a little bit first. Okay, then on the one hand, polar factorization tried to do this. On the other hand, we have this optimal transport problem, and somehow this mapping T is coming out of it. Where does T fit onto this diagram? It goes the other way. Yeah, so T was the optimal mapping from mu to nu here, right? And we know when we do optimal transport, T was going to be written as the gradient of phi. Okay? The phi and c are Legendre duals. So what are we going to have? We're going to have that. This way, we're going to have T, which is the gradient of phi, because these are Legendre duals. Okay, and just to have these here, I'll write down the factorization that we came up with, grad c of s of x. And s of x was grad phi of r of x. And those just came from these things being Legendre duals. So let's see, does that look good? This was the thing we drew first. R we could decompose as grad c of s. And here, S, the map from here to here, is decomposed as grad phi of R. So this, I think this diagram is right. I think this makes sense. All right, so let's go back to our objective function and see if we can rearrange it a little bit to see where our polar factorization somehow fits into here. So our objective function for the optimal transport problem for OT is x minus t of x squared d mu of x. If we want to play with this a little bit, rewrite it a little bit, okay, the freedom I have here, as before, is in the measure, right? So what do I know about this measure? What I know about this measure is actually written over here. But we also know that t is intimately connected to the measure. Let's use this fact, though. So if I have some function of x, and integrated it against d mu of x, I could replace that function with r of x. So everywhere I see an x in there, I could replace it with an r of x, and then I'm back in dealing with the Lebesgue measure. So this is the same as r of x minus t of r of x dx. Right? This was the definition of mu. And what's another name for T of R of x? S of x, exactly. So we come back to here, T of R of x. So here's T composed with R. That goes there or there. That's the same as S of x. You can see it here too where we've written it. Grad phi is equal to T. So T of R of x is S of x. That's our measure preserving rearrangement. So this I can write as R of x minus S of x squared. Okay, so in other words, the thing we're trying to minimize is equivalent to this. R is given. S is an unknown. We want to minimize this. Okay, over measure preserving rearrangements S. Okay, so R is given. S we want to find. Oh, what does this look like? If you see objects like this. What's that?
It's like
A metric, or what else? I'm trying to minimize this. Subject to S belonging to a space that I care about. So this should hopefully remind you of a projection, right? You gave me a vector field R, just whatever R you wanted. Now I'm saying, okay, well, let me try to find a measure preserving vector field that's as close as possible to this R in this L2 sense. That's projection, right? So what you're really asking me when we're doing polar factorization and we want this measure preserving map S, so we are looking for S S sort of as close as possible to R. I'll call this measure preserving. So an interpretation of this is, or we could say that S is the projection of R onto the set of measure preserving mappings. Okay, so you gave me a vector field R that you cared about, which is maybe crazy. I said, this is a little too hard to deal with. Let me project it down onto a set that's easier to work with. A set that's easier to work with are vector fields that preserve measure. So I project it down onto this set, and now I said, now I've got something that actually I can characterize as the gradient of a convex function. So this is another interpretation, I guess, of polar factorization. As I can't write the vector field you gave me as the gradient of a convex function, but if I project it onto the right set, now I can write it as the gradient of a convex function. So it's different ways to think about the same thing. Again, Brittany was motivated. This was the problem Brittany cared about, is you gave me a vector field, how can I project it onto the set of measure preserving mappings? And he was looking at problems in fluid dynamics, actually, when he did this. But there's a lot of connections that I can see some of your heads are spinning trying to keep all this straight. There's a lot of interesting connections with optimal transport and taking the same problem and viewing it from a few different angles. Any questions on that? If not, I'm going to leave it there today. Next class, we're going to start looking at the Mogent-Pair equation. So we'll probably spend the next week or two looking at the motion pair equation, some of its connections to optimal transport, which we've seen a bit, different weak interpretations of the equation, and learning more towards probably a goal of how could you understand this thing numerically, and actually how could you compute solutions to the optimal transport problem.